Hello and welcome once again for another EE324 video, and today we will be doing an example problem for day 5. For water, determine the specific volume at the indicated state in cubic meters per kilogram. Locate the states on a sketch of a TV diagram. Okay, so we have three parts: Part A, Part B, Part C. Part A is with a temperature of 400 degrees Celsius and a pressure of 20 megapascals. Part B is 40 Celsius, 20 megapascals, and Part C is 40 Celsius, 2 megapascals. So this will be good for us to learn how to navigate the tables. So the first part, we have a pressure of 20 megapascals and a temperature of 400 degrees Celsius. Now, if you were to go to the table A2, which is the saturated table in terms of temperature, you would find that the pressure you would find something interesting about the pressure, which makes it hard to find on the tables. So basically, when we're navigating these tables, the best thing to do is to examine which tables give us easiest access to the information that we're looking for. So in this case, you can probably guess, because there's a high pressure and a high temperature, that we probably are in the superheated vapor region. We have to verify that that's the case, but immediately you should be thinking, if you have high pressure and high temperature, the combination of the two, you're probably in the superheated vapor. So this is actually the superheated vapor table A4 in your textbook. Now, we can verify that it actually is a superheated vapor, and I'll show you how to in a moment. So I'm going to go down, and notice that this is only part of table A4, by the way. I just took out the part that I needed because it has the temperature of 400 degrees Celsius, right? That was what we were looking for in this part of the problem. And the saturation temperature is actually listed in the superheated table. Really convenient. And notice that the saturation temperature, this is actually only 16 megapascals, so it's not quite where we want yet, but we'll scroll down to where we want in a moment. But already at 16 megapascals, we're above the saturated temperature. Now let's go down to the actual one that we want. We want 20 megapascals, which is the same as 200 bar, right? So here's the actual part of the table that we want. And the saturation temperature here, notice, the saturation temperature at this pressure, this is table A4, at this pressure, the saturation temperature is 365.81 degrees. Now again, we could have had a situation which would have led us to have to go back to the saturated tables. If we had come in at the saturation temperature or below the saturation temperature, we might have to back up to those tables, okay, or to the compressed tables, depending on the situation. But in this case, our temperature is greater than the saturation temperature. And recall that we already identified this as a scenario where we're superheated. So since we're using the superheated vapor table, we're in good standing here. The saturation temperature is lower than the temperature that we were examining. Very good. Now let's go back up here and figure out what we're looking for, which was the specific volume. And remember, specific volume is this lowercase v, this thing right here, in meters cubed per kilogram. So if I come down here I have 400 degrees. So I'm going to erase all this stuff up here now, except for that. I do want to keep note of that. So if I come down here on this table, I see that way down here, this is the specific volume that I'm looking for. Okay, and notice that this one is listed in cubic meters per kilogram. We're going to have to be very careful with this, as we'll see in a moment. But this is listed in cubic meters per kilogram, so we're good here, and we can literally just read off of the table. So the answer here is 0.00994 meters cubed per kilogram. Okay, very good. Now part B. We're still at 20 megapascals, but we're at 40 degrees Celsius. Now immediately going back to the superheated table, we know that that's below the saturation temperature. Since it's below the saturation temperature, in fact, it's far below the saturation temperature here, that is probably going to indicate that it's likely in the compressed region, right? In the compressed liquid. Because of how much lower it is than the saturation temperature, which was 366 Celsius. So it's much lower than that. So for part B, I actually grabbed, this is the compressed, this is table A5. And this is the compressed liquid table for water. Should mention all of these are for water because that's specifically what it indicated, right? For water. But you could have other things, and there are other tables associated with refrigerants and other things like that. So just be aware of that while you're... I definitely think you should take a look at all these tables. They're in the back of your book, and you can find them hopefully relatively easy in the back of your book. But in any case, this is table A5, and I was looking at 40 degrees Celsius and 20 megapascals. Okay, so table A5, I have 5 megapascals there, 10 over here. Here we go. We're at 20 megapascals. And again, of course, we're below the saturation temperature, so we can actually come here and say, okay, we probably want the compressed table. And look at that, we have a nice value there, which means I have to come across here. And let's just double check. Yes, we have this. Okay, so now we have to be careful. Notice that before up here, it was just meters cubed per kilogram in the superheated vapor table. But here, it's times 10 to the third. So that means that if we want to undo that times 10 to the third, we actually have to multiply the value that's shown here by 10 to the minus 3. So this is something that we're going to have to keep in mind when we're dealing with these tables. So this is the specific volume, and it's right here. That's my answer, 0.9992, but I have to multiply by 10 to the negative third. Meters cubed per kilogram. And again, that's because what they did is they multiplied the value here, because the number was so small, to save space on the table, they multiplied it by 10 to the third, just in order to save themselves some space. So you have to undo that by multiplying by 10 to the negative third. Okay, very good. Okay, well now what about part C? Okay, again, we're at 2 megapascals and 40 degrees Celsius. Now if I go back up here, I don't think that I have it. Yeah, okay. So table A5, actually, the lowest value that is listed is actually 2.5 megapascals. And we're looking for 2. Now, there's actually a trick with this because it is in the compressed liquid regime again, remember? It's definitely below the saturation temperature. But if it's not high enough pressure to make it onto the compressed liquid table, we can, and you'll see this in a moment, we can actually assume that the value is close to the saturated liquid value, and you'll see why in a moment. Okay, so let's go. This is the saturated table. This is table A2, and this is saturated water. Table. And it's the temperature one. There's also a pressure one, so if that's more convenient to use, you can. But in this case, I think it's more convenient to just go directly to the temperature. So we have 40. And again, the pressure here is quite a bit actually higher than the saturated pressure. So that definitely indicates to us that we're in the compressed regime. But what I said to you was, actually, we can just use the saturated liquid, which is VF here. This is the saturated vapor, and over here is the saturated liquid. We can use VF here. And again, this one also has that. Notice that only the liquid side has the multiplied by 10 to the third, whereas the vapor side does not have that. So you have to be careful when reading these values. But only the saturated liquid, or the saturated liquid value ends up being 1.0078 times 10 to the negative third. And I'm going to take that to be the value here. And you say, well, hold on, why am I doing that? Why am I taking that value? Well, look just here, going from 2 megapascals all the way up to 20 megapascals. In the compressed, both of these are compressed liquids, right? Both of these are the compressed. Look at the difference between this one and this one. Not much difference, very tiny difference, right? So even when you have very high pressure, the liquid does not compress a lot. In fact, that's why we tend to say liquids are incompressible, okay? So the compression is very small. And so it's okay in that scenario, especially when you don't have something that you can read off, and you can't do any kind of interpolation in that case because you don't have a value on the other side of it. You could do some interpolation if you really wanted to by going back to this table, and then and then also using the compressed liquid table, but it doesn't make a lot of sense to do that. There's not going to be a whole lot of change. It's not going to be very wrong to just assume in this case, especially since it's just 2 megapascals, that this is the actual value. So we're going to say it's approximately, we'll put there. Okay, so that is the value that I get. That's all that I have for this video. Hope to see you again soon.